Welcome to The Explainer. Today, we're diving into something that literally every organization deals with: data. And let's be real. In the wild, data is messy. It's incredibly messy. It almost never lives in one giant, perfectly organized spreadsheet, right? Instead, it's usually scattered across all these isolated, disconnected tables. It's siloed. And that presents a massive challenge when you're actually trying to, understand what on earth your data is trying to tell you.
So, it brings us to this really fundamental question. How exactly do databases connect all of that scattered, isolated information into one unified, meaningful view? Learning how they do this isn't just some boring technical requirement. Honestly, mastering this exact skill is a true data superpower. When you're dealing with the messy reality of disconnected systems, you absolutely need a reliable way to weave those separate threads of information together.
The solution to that messy data problem? It's something called a join. In a database management system, a DBMS, a join simply combines rows from two or more tables based on a related column between them. You can think of it as the ultimate structural solution. It's the bridge. It brings disparate pieces of information together. So instead of just staring at isolated lists, a join lets you define exactly how those lists relate to one another to form a complete, big-picture view.
Okay, let's dive into this. Here is our roadmap for today. First, we'll meet our database tables. Second, we're going to look at the inner join for perfect matches only. Third, left and right joins explained. Fourth, full outer and cross joins. And finally, we'll wrap up with the ultimate join summary.
All right, part 1. Let's meet your database tables.
Every good data scenario needs some characters and a problem to solve, right? So here is our first isolated set of data, the student table. We've got 3 distinct columns here: student ID, name, and department ID. We have Alice, whose department ID is 101. We have Bob over in 102. And then, we have our friend Charlie. Charlie's student ID is 3, and he's assigned to this mysterious department ID of 103. Keep that number, 103, in the back of your mind.
Now let's look at our second table, the department table. We have Dept ID and Dept name. 101 is computer science, which matches Alice perfectly. 102 is electronics, matching Bob. But look at the tension here. That Dept ID 103, Charlie's department, doesn't exist in this table at all, just completely missing. And furthermore, we have Dept ID 104, the mechanical department. But looking back at our students, absolutely 0 students are assigned to 104. Basically, we have mismatched data.
Moving on to part 2, inner join, perfect matches only.
So how do we actually query this mismatched data? Well, an inner join has a very strict, almost unforgiving rule. It returns only the matching records from both tables. If a piece of data in one table doesn't have a corresponding, perfectly matched partner in the other table, based on the column we specify, of course, it simply doesn't survive the process. It is completely, 100% filtered out.
And here's what that looks like in actual SQL code. We're asking the database to select the student's name and the department's name. We start from the student table, and we inner join the department table. But the real magic, that happens right at the end. On student.deptID equals department.deptID. We're explicitly asking the database to link these two tables exclusively via that shared DeptID column.
And here is the result. As you can see, Alice and Bob found their perfect matches: computer science and electronics. But look at who's missing. Poor Charlie is left out in the cold. Because his department ID of 103 was entirely missing from the department table, the inner join just dropped his record completely. It wasn't a perfect match, so poof, it's gone.
Which brings us to part 3, left and right joins explained.
Now, sometimes you really don't want to lose data just because there isn't a perfect match. What's really interesting about this is how these two next joins act as kind of opposite lenses on the exact same underlying data. A left join ensures that all records from the left table are returned, alongside whatever happens to match from the right. A right join, it flips this entirely. It returns all records from the right table plus whatever matches from the left.
Let's take a look at the left join query. The structure is almost identical to our first query, but the foundational difference here is the command left join. Remember, the table we specify first, in this case student, right after the from clause, is inherently our left table. Basically, we're telling the database, hey, do whatever you have to do, but absolutely do not drop anyone from the student table. Because we protected that left table, look at our result. Charlie is finally included. The database kept all the students. But since there's still no matching department data for his DPT ID of 103 in the right table, the database simply fills in his DPT name with null. It acknowledges his existence, even if his associated department data is completely missing.
Okay, now let's pivot and look at the right join query. By swapping out left for right, we're essentially shifting our strict priority. Now the department table, which sits on the right side of our join statement, becomes the VIP. We're telling the database not to drop any departments, regardless of whether any students are actually assigned to them.
Look at how the data morphs here. Because we prioritize the right side, the previously empty mechanical department now proudly appears in our results set. Since no student matched its DEPT ID of 104, the database just slaps a null under the student name column. And, well, because we're no longer protecting the left side, our friend Charlie gets dropped completely once again.
All right, building some momentum here. Part 4, full outer and cross joins.
We've looked at strict matches, we've looked at prioritizing one side. Now let's transition to the most expansive tools available to us, starting with the full outer join. This query applies the ultimate inclusive rule. It asks the database to return all records when there's a match in literally either table. It's effectively combining the power of the left join and the right join into one single, overarching, massive command.
And this brilliantly illustrates the true power of a full outer join. Every single piece of data now peacefully coexists in one massive result. Alice and Bob, they have their perfect matches. Charlie is preserved with his null department, and the mechanical department is preserved with its null student. Nothing is lost. Absolutely every row from both initial tables is totally accounted for.
But there's one more, highly unique tool we need to discuss, the cross join. Notice in this query, there's no on clause. We aren't linking them by DEPT ID at all. That's because its rule is honestly kind of radical. It creates a Cartesian product, meaning it matches every single row of the first table with absolutely every row of the second.
Because we have 3 students in our student table and 3 departments in our department table, this multiplier effect means our final data set will result in exactly 3 times 3, or 9 total rows. Alice gets paired with computer science, electronics, and mechanical. Then Bob gets paired with all 3. Then Charlie gets paired with all 3. It just generates every possible combination between the 2 data sets.
And finally, Part 5, the ultimate join summary.
Wow, we have covered a lot of ground today. So, here is your ultimate logical data wrangling cheat sheet. So the crucial point is that each specific join solves a very unique data problem. The inner join is for when you only want the matching rows. The left join preserves everything from your primary left table plus matches on the right. The right join just flips that, preserving the right table plus matches on the left. The full outer join is your safety net. It returns absolutely all rows from both tables. And the cross join? That generates a Cartesian product, mapping every single row to every single row.
You now have the exact structural framework required to turn messy, isolated information into clear, actionable insights. By understanding how to connect these tables logically, you're no longer at the mercy of disconnected systems. So, I'll leave you with this provocative thought. What real-world, messy data will you conquer next with your brand new querying superpower? Thank you so much for joining me for this explainer, and I can't wait to dive into our next complex topic together.